So remember that the purpose of collector is to collect the electrons. So that's the only purpose. You basically need to collect these electrons. The purpose of emitter is to emit the electrons. Emit is pushing or injecting. So let me again, for the sole discussion entirely, we're going to rely on the NPN. So again, all the concept that you will be seeing is from the NPN perspective. So that's an N-type region. That's P-type, and that's the collector. So this one is NPN. From the terminals perspective, emitter, base, and collector. So we know from the semiconductor perspective, N-type means you have very rich in negative. So if you carefully observe, I draw this P region very small, but the collector is very large, whereas the emitter is moderate. So the width of these regions will be like this, but the doping concentration for the emitter, the doping level is extremely high, meaning that you're going to find a huge number of free electrons that are wandering in the emitter region. The doping concentration is extremely high. Remember, what is the purpose of emitter? Emitter means it is designed to emit the electrons. So it's basically a source of electrons. Whereas the collector is also N-type, meaning that collector is also having electrons, but collector region is usually moderately doped. So the doping concentration for emitter is heavily doped. For collector, what we say is a moderate. Base is lightly doped. And of course, there is reason for all these three. Again, the purpose of heavily doping is because emitter is supposed to act as source of electrons. And whereas the thickness goes, importance should be given to the base. Base is very thin region. So, which will come evident down the line when we talk about how the transistor really operate, then we will see the need for why the base should be very thin. That's why you see that the width of the base I draw extremely small. It's not even going to be like that. It's very small. But for basic operations, I just used it. But remember, P-type is you have holes, correct? So the charges you see here are only majority charges. Meaning that, remember, an N-type, we know it has an extremely high number of electrons, but also very small holes as well, correct? What? Again, remember that's a PN junction, correct? So how does a PN junction operate? In order to have a current, the junction should be what? What should we need to do? And you're already forming a junction. The emitter and base were already together. You form a PN junction, correct? So how does a PN junction allows the current? Under what condition? How? So you basically forward bias the junction. This is a PN junction like a diode. Instead, it has two PN junctions. How a PN junction operates, that's how each PN junction operates here. Except you have two PN junctions to talk about. So under no voltage, so let's say you don't apply any voltage, like in traditional PN junctions, you're going to develop some barrier, correct? Is that true? Because now you have electrons on the emitter and holes on the base, right? Since the junction is at the instance of junction formation, the junction is very thin, so the electrons and holes will jump from here to here, right? So I'm not doing anything yet. What? So the junction will be wider a little bit on either side. Let's say something like that. Correct? Same thing happens on this side of the PN junction as well. Right? So since the N type is a moderate, so you can have something, but definitely there is going to be certain barrier potential. That means if you're testing the transistor, like you test the diode, remember how much voltage you should see when you forward bias a diode? Ideally 0.7. Exactly when you test a transistor from base to emitter, remember base is a P, emitter is an N. So when you test the PN junction between base and emitter, you should read 0.7. When you test between base and collector, how much you should read? Again, that's the PN junction, P type, N type. You're going to see, you see close enough to the 0.7, maybe a little bit smaller. Base to emitter. We are only testing PN junction wherever you see a PN junction, which is only happens between emitter to base. That's one. Another one is base to the collector. It doesn't matter. If you forward bias, then you put your multimeter on the base, which is a positive. You put your positive lead on the base, negative on the collector. And one on the collector. Yeah, it should be 0.7. Either you go from base to emitter or base to collector, because both sides it's a PN junction. Right? So a working transistor or a good transistor indicates this. So next, obviously without any source, you're not going to have any flow of electrons from one side to another side. So now this is a requirement and this is a must for a transistor to operate. Let's say, for example, you want to forward bias the first junction. Let's say I'm going to call this junction as J1. How can I forward bias J1? So the base, since base is a P type, if I want to forward bias the junction, the base will get a positive because it's a P type, N type gets a negative. That forward bias is the junction J1, correct? So assuming that you have enough voltage, which is, remember that at least you require 0.7 to overcome that barrier. Let's say you overcame that barrier, then definitely there is going to be some current conduction will be happening, meaning that this side is negative. So that means from the source, negative electrons will be entering this side, correct? Which will repel the electrons that are already in the N region. So all these electrons will carry over the barrier because you are forward biasing the junction. Some of these electrons, and this is the reason why the base should be very thin. Again, remember the main intention of the operation of a transistor is to carry the electrons in the emitter all the way to the collector. So if the base is very thin, so when these electrons are going to the base region, we don't want them to recombine with the holes, provide a net charge of 0. We don't want that recombination because we want these electrons to carry over all the way to the collector. So the purpose of very thin base region is to minimize the recombination, because if you recombine, if the base is very large, then all these electrons from the emitter will be replacing the holes, which is the recombination. They're not going to be carried over to the collector. So again, the purpose of very thin base region is to minimize the recombination. Between emitter to the base, between the emitter and base. That's why the base is only a transport medium of these electrons. It's like a channel that will allow the electrons. But if you put more holes into the channel, then all these electrons will recombine and they're not going to be carried over to the collector. Again, main purpose is to take this huge number of electrons onto the emitter, all the way carried over to the collector. But in order to do that, you require to overcome two barriers. One barrier is between base and emitter, another one is base to a collector. So when you overcome, let's say the base, when you have the voltage on the base at least 0.7, now the junction J1 will be forward biased. Now some of these electrons will go into the base. For example, if the base has like 10,000 electrons, sorry, the emitter has 10,000 electrons, base is like only 100 positive, 100 holes, meaning that off of that 10,000, only 100 will recombine and you're remaining with 9,900. That's plenty to be carried over to the collector. So that's the purpose of having a very thin region on the base side. So the rest of the 9,900 electrons will be providing some base current. So whatever that current is, because now you forward bias the junction, now you are definitely going to have some current going through the base, which basically the current flow will be like this. Whatever that current is, depending upon how much source you are feeding in. There is always a requirement in transistors on how much base current you need to supply to forward bias that junction. As long as the voltage is above 0.7, you have enough voltage to forward bias the junction. So that's the first junction. It must be forward bias, meaning that the base should get 0.7 volts compared to the emitter side. So are we clear on that side? So that's why usually on the base, all we need to make sure is you have either 0.7 or not, or more than 0.7. And if you have it, what we say, the transistor is turned on. That's the requirement and must for an NPN transistor. The base must get a positive 0.7. Then what do you think for PNP? Negative 0.7. As I mentioned, PNP is exactly opposite to the NPN. So if the base requires positive for NPN, then PNP requires a negative. So the base emitter junction must be forward bias. So we get the next junction, which is happening between what? The base and collector. That junction must be reverse bias for proper operation. So the base collector must be reverse bias for proper operation. Yep. So, all right. So let me quickly just raise this. Give me. So that's. So base to collector must be reverse bias. So base is P type, meaning that base gets negative, whereas collector gets positive. Correct? Is that reverse biases junction J2? Because P will be on negative side, whereas N will be on the positive side. So that will definitely reverse biases. And as we learned before, what happened to the depletion region when you reverse bias a junction? Does it narrows or widens? So the depletion region will definitely be wider between base and collector, right? But here is the question. So if that junction J2 is reverse bias, how can I carry over all these electrons on the emitter all the way to the collector? The key to that is what source am I using? That's exactly correct. If you put very high voltage, usually you're talking about like 10, 15, all the way to 40, 50, 60 volts on this supply right here, which is happening on the collector side. So if you put extremely little bit higher voltage on this side, then you see right here, this is a positive, correct? Then it's going to attract the electrons that are already in the collector. But also, since this is a heavily very high in the voltage value, it is going to pull, because remember, these electrons are now moving in this loop, correct? So now these electrons will be pushed over all the way to the collector by overcoming the thickness of the depletion region, because the supply you are using on the collector is going to be higher. Since the supply voltage is higher, it is possible to overcome that barrier, because all these electrons now pushed into the p-type, which will repel, which will push us the electrons that stick in the base all the way to the collector region. That's from the majority carrier's perspective on how to overcome the barrier under reverse bias between base and collector. So that's how the majority carriers work. In this case, we are purely talking about the electrons on either side of the n-type material. So that's how. So this junction must be forward bias between base and emitter, meaning that you require at least 0.7 volts right there. This junction is usually reverse bias, so depending upon the limits, you can put 1 volt, 2 volts, 3 volts. Of course, with that small voltage, you're not going to have any current. But so that's the electron current. So now you're going to have current basically emitter to the collector. But something will be happening, because remember that we say the type of transistor is a BJT, and we mentioned that BJT, B stands for bipolar, correct? So what is bipolar means? Bi means what? Two. Polar means? It's a polarity, correct? So in the last discussion we mentioned, okay, in order to current flow through the PN junction, the junction must be forward bias, which should have a voltage of at least 0.7, which we usually called as VBE. So what do you think that means? What is B for? It's base and E for emitter. So that VBE stands for voltage between base and the emitter should be at least 0.7 to forward bias that first junction. So in order to have some current, we need to close the depletion region of base and emitter. So some of the electrons, so for example, since this is positive and negative, so all these electrons on the emitter will go attract towards this way with minimum recombination, correct? But also remember that does N-type means only electrons? Because you're going to have a little bit of positive here. What about P-type? Same thing, but you're going to have a little bit of. So this is where the term bipolar came in. So now we are saying that all these electrons will go towards the supply like this. What about the minority carriers, which are electrons here and the holes here, because part of this current will be towards this way as well, but that current is extremely going to be small. So now you have an electron current and also you're going to have hole current, but electron current is extremely high because the doping concentration of emitter is extremely high. So all the electrons in the emitter region will push towards the base region. You're going to have very small current onto the base region. So from the base perspective, the current is extremely small because the only voltage you need to overcome is the barrier. But now when you connect another supply between the collector, which is, so that's probably shows you the electron current and the hole current, which are exactly opposite to one another. That's why the name bipolar, the term bipolar is indicating that the current conduction is because of both charge carriers. Because there are extremely small hole current, but very huge electron current. But usually we don't take hole current into consideration because it's a very, very small. We're talking about it like in nanoamps. But the other junction would be something like this. But in here, we need to reverse bias that junction where collector gets positive. Remember, collector is an N-type semiconductor, but here you are putting positive. So the name of that supply is called as what? C and A, which is collector to the emitter. So assuming that you have proper base voltage, that means this junction is already forward bias. And this junction right here, based on the depletion region, you can see the thickness is very high compared to the other one. So that's reverse bias. So if you have high voltage here, where we reverse biasing the collector junction, so positive polarity on the collector will attract the electrons that are already in the collector, but also all these electrons that stuck into the base will be carried all the way through the collector. So that means all you need is, this is the advantage of a transistor, is all you need is very small voltage on the base, which has a capability to control large current that is going from emitter to the collector. And always remember that base current is always going to be small. What do you think will happen if I put very high current through the base? You can damage the transistor, because remember that the base is a very thin region and very lightly doped. It cannot handle a lot of current. Right? So you cannot have consistently a lot of current in the base region. So the advantage of transistor is all you need is very small current on the base, but you can control the current on the collector side. And the load will be placed somewhere here. Load on in the circuit on the transistors is always from the collector perspective. Like for example, you can have a motor, you can have a lamp, or whatever that device is. Yeah, small voltage which gives you very small current, correct? So before you quick, it's two PN junctions. That means it's like a two diodes back to back. It can be visualized like that, but you cannot make a transistor by simply taking the diodes, because in a diode the doping concentration is same for p-type and n-type. Transistors can be visualized as a two diodes back to back, but that doesn't mean that I have two diodes, I can make my own transistor, because internal doping concentrations are going to be different. So, yeah. So yeah, it can be visualized like that. Definitely. Two PN junctions, because PN junction is nothing but a diode, correct? So which source we are talking about? If the base, the requirement for NPN, right? If you want to turn the transistor on for NPN, the base should get more than 0.7 or at least 0.7. Which source you're talking about? There are two sources here. Which one that you're referring to? You're referring to the VBE side of it? Yeah, if you put like 1 volt right here, you're still more than 0.7, you're still good. You see what I'm saying? You can have it, but not too high. That's not a requirement. For example, why would you require a very high voltage if you can use a low voltage? See what I'm saying? Because low voltage, you're going to have less power consumption and less heat. You see what I mean? So base controls little bit of current, but it's not needed. Depends on application. You don't necessarily need to put a very high current through the base, because some transistors can easily be damaged. For example, if the requirements say, okay, base should get at least 100 microamps, right? Then that's all we aim for the design. Unnecessarily, we don't go for high currents on the base because it's not a requirement. Firstly, you may get overheat the base. That may effectively damage down the line. If you are overheating it, then you are wasting the power from the battery, correct? Base has nothing to do with VCE. Those are two separate things. The base voltage has nothing to do with the VCE. VCE is on the collector side. VCE, you can put any value of your interest depending upon what your load is. VCE, you can choose any value that you want depending upon what your application is. So for example, let me give you this practical circuit. Let's say I have a lamp that I want to turn on. Let's say I choose an NPN transistor. Let's say I have a lamp that I want to turn on. So what I do is I take this lamp and connected this lamp. Remember, this is collector, this is the emitter. So I'm going to call this as, again, this is the supply that is on the collector. Again, the terminology we're going to talk about later on. This is actually called as a VCC. Yeah, that's pretty much your battery. So this is your VCE, correct? So on this side, this is what the actual application of a transistor is. Let's say you have a voltage of at least 0.7 on the base, correct? Yes, you require two voltages. One is from the base perspective, which decides whether the transistor is going to be on or off. Second, you require the collector voltage to turn whatever the load that we are working. The load could be a lamp, a motor, or a speaker. You require both voltages. But how do you provide them? That's up to us. But you require two voltages. Base must get positive 0.7. So let's say you provide it. So what will happen is now it closes the circuit. So now it's pretty much the current will flow through this loop only. So you are controlling this side of the circuit if you have the enough base voltage. Think about the transistor like a switch. Let's say I have the same lamp here with the same source here. Let's say this transistor is like a switch where the switch can be controlled by the base. So if you have the base voltage not 0.7, if you have like lower than 0.7, then the transistor acts as an open circuit where obviously you can see that the current cannot go through. But once you close that, that means once the base reaches 0.7 volts, now transistor is acting as a closed circuit. Now you're going to have full current flow on this side. Does that make sense? So controlling an electrical signal on one side, you are controlling an external circuit on the other side. With a very small voltage on one side, you can control large voltages on the other side. Yeah. Once the 0.7 is on the base, you see the 0.7 is on the which terminal? It's on the base. It's the what load requires.